hope everyone's having a good day. I saw that everyone finished part 1 of the test. Don't forget that part 2 of the test is due tonight by midnight, basically 11:59 p.m. I noticed that probably 2/3 of you have that done already, so the rest of you make sure you go ahead and get that finished as well. We're going to start chapter 8 today. Just wanted to note that we're going to skip 8.1 and we will skip 8.7 as well. So we'll cover 6 sections in this chapter, so that's 2 through 6 and then also section 8. So today we're going to start in section 8.2, which is on integration by parts. As far as the tests go, I'll probably have those graded by, I'm hoping by Monday, definitely by next Tuesday though. And it may go faster than I think, but we'll see. Okay, as I said, starting in section 8.2 on integration by parts. Now, so far, anytime we've had a product of terms inside of an integral, we know that in order to integrate a product, we have to either do like a substitution or somehow resolve that product. But most of the time it's going to be a substitution of some kind. Now, starting in section 8.2 with integration of parts, it actually adds another alternative for us in these types of problems. So, integration by parts can be used when we have two different types of functions being multiplied or divided in an integral. Okay. Now when we say two different types of functions, specifically types of functions that we are referencing here, we could have a polynomial function, we could have a logarithmic function, could be exponential, it could be that we have a trigonometric function, or it could be that we have an inverse trigonometric function. Okay. So the idea is that we might have a product or a quotient of two different types of functions here, like we might have a polynomial times a logarithm, a trig function times an exponential, a logarithm divided by a polynomial, inverse trig divided by a polynomial, that kind of thing. So there's some combination there. And it may also include, like, we may also have like square roots present, which is not exactly polynomial. Now, that's actually a good point. I wanted to bring it up. Instead of polynomial, it might be better to say what we call algebraic functions, which would then incorporate square roots into the list. So algebraic is probably a more accurate term instead of polynomial. Most of the time, though, we will see polynomials rather than things with square roots and such. The only time we really see like the square roots is when we have an inverse trig function, by and large, because the derivative of inverse trig functions tend to have square roots involved. 4 out of the 6. Anyway, generally, though, it will be polynomial, and so for the most part, that's what we see. Let me give you an example of problems where we can use integration by parts. And I kind of talked about this already, but we could have something like x squared times e to the x dx, integral of x to the fourth natural log of x dx. Even just the integral of natural log of x by itself, that's actually an integration by parts problem. You may have noticed that up to this point, we've talked about the integral of 1 over x, which is natural log of x, but we've never actually integrated natural log x itself. And that's because we haven't really had the tools necessary to do that prior to this point. So we could have e to the x times cosine. I'll just use e to the x cosine x. I don't want to make that one too crazy. I mean, we could make these a little bit more complicated. Like I could say e to the 2x there. This one's kind of a crazy problem anyway, so I don't want to go overboard. But the idea is that we have a mix of two different functions. Like we have a polynomial and we have an exponential. Or we have a polynomial and logarithmic, or just a logarithmic by itself. And then an exponential and a trig function. We could have x cosine 2x dx. What else? Let me find one more that involves inverse trig, and these will be the examples that we work through. X arcsine of x squared dx. And one more I have to do. It's generally required for any Calculus 2 course. Is integral of secant cubed, which is kind of a doozy, but we'll do it. Okay. So, each of these, move this before it falls somewhere. This throw it on the floor. That'll solve that problem. Okay. Each of these is a combination of a product of two different types of functions, and this is exactly the case where we would like to use our method of integration by parts. So we have, like I said, polynomial and exponential, polynomial and logarithmic, just logarithmic by itself, exponential and trig, polynomial and trig, polynomial and inverse trig, and then weirder trig integrals will also require integration by parts. And secant cubed of x falls into that category. Okay. Let me go ahead and make that a 2x just to make it a little more interesting. Not too much more interesting, not a little more interesting. Alright, so let's look at the method of integration by parts by itself. Now, in an integral, so let's say we're given an integral there's going to be two elements to this integral that we want to identify. We want to identify which element is called u and which is dv. Okay, because the idea is that we start with integral of f of x dx, which will simplify as integral of u times dv. Okay, so our first step is to identify from this integral, whatever integral we begin with, which term is u and which term is dv. Now we actually have a nice little guide as far as how we can find which one is u. So this is choosing a function to be u, and the mnemonic we have here and sometimes you see slightly different variations on this, but it's Lipet, L-I-P-E-T. At the top we'll see our first choice, and at the bottom we'll see our last choice. So Lipet, that's a logarithm. If there's a logarithm present, we always want it to be u. Okay? We'll always choose our logarithm to be u. That's our first option for choosing u. If there is no logarithm, but there is an inverse trig function present, then we would want to choose that as our u next. If there's neither a logarithm nor an inverse trig function present, our next option is the polynomial. And if we don't have any of those, then our next option is exponentials. And finally, our last choice would be trigonometric functions. Now, exponential and trigonometric actually could be interchanged there. The main thing we want to have is a consistent ordering. That way we keep choosing which one we do first as u consistently. So if we have exponential and trig, let's just keep using exponential first and trig second. And I made sure to include one of those examples to go over that. All right, so I mean this tells us which way we can go with what's our u substitution and then what's our dv substitution. Now, going back to that list of problems we started with, the first one I wrote down was x squared e to the 2x, which you can't really see there. Okay. Dx, sorry. So, our task is to choose which one's going to be u and which one's going to be dv. Now our guide is if there's a logarithm, we choose that first. There's no logarithm here. Next, if there's an inverse trig function present, we would choose that next. We don't have inverse trig present. Our third option would be a polynomial, and we do have a polynomial x squared, so we would choose u equals x squared, and then dv would then be everything else, e to the 2x dx. Okay. So again, we've split this integral into two parts, u and dv, which represent the two pieces of this product. Now, once we identify what u and dv are, we have to find du, which is the derivative here. So the derivative of x squared is 2x dx. And then we have to find v, which is the integral of e to the 2x. And the integral of e to the 2x is 1/2 e to the 2x. Normally we would put plus c there, but in this case, when we're working with integration by parts, we would leave off that plus c, because it'll be taken care of later. Okay. So we started with u and dv, we differentiated u, we integrated dv to get v. So that now gives us four pieces, u, du, dv, and v. Now let's look at the formula for integration by parts. Okay. It turns out if we have the integral of u times dv, this is equal to uv minus the integral of v times du. Okay. So what this does is it gives us a way that we can rearrange these terms, like, okay, we know this is u and this is v, so we'll plug them in here, u times v, minus, and then we still have to integrate v times du. So that'll be the product of these two terms here. And so that's the general principle. Now, as far as, when we eventually get to a test for Chapter 8, you will need to know this ordering here as far as how we can choose u. So if you want to memorize or start using that mnemonic, you'll probably get it figured out pretty quick. You'll also have to know this formula for the integration by parts, so that will not be given to you. Alright, let's look at this formula a little bit more closely. It may not resemble anything that we've learned up to this point, but it actually is based on something that we did learn from Calculus 1, which is the product rule. It's entirely based on the product rule. Specifically, let's look at the product rule. I don't know what happened there. Product rule. Let's say y is equal to u times v. And then y prime, our product rule says we take the first term times the derivative of the second, and then we add, and then we take the derivative, keep the second term times the derivative of the first. Now, since we're saying y is equal to u times v, then y prime, we could say, is the derivative of u times v. Okay, so instead of saying y prime, we'll just plug in y with a prime on it. Next, we'll integrate both sides. By integrating the derivative, that's just going to give us u times v. And we have integral u dv plus integral v du. And from there, it's a matter of manipulation of terms. And we can arrive at the formula, which is the integral of u times dv, getting this term by itself is equal to uv over here minus the other integral. And that right there is our integration by parts formula. So what's really happening then is that the integration by parts is basically reversing this product rule operation, where we have an answer, that we're trying to integrate. We have an expression we're trying to integrate that the product rule had previously been applied to, and a lot of terms had canceled out, and we need to work backwards to find the original function by integrating. And so that's the process. Okay. So now that we have our formula for the integration of parts, let's look at some of our examples that I wrote down. Okay, first, and this is the same one we already talked about a little bit, x squared times e to the 2x dx. Now we already said that u should be x squared and dv should be e to the 2x dx. So again, it's just splitting up the terms here into either u or dv. Everything should be represented one or the other, but not both. We then decided that the derivative of u is 2x dx, and the integral of the integral of dv is 1/2 e to the 2x. Now, according to our formula, the integral of u times dv is equal to u times v minus the integral of v times du. So basically, we're taking these four terms that we found and arranging them in this formula. So u times v is x squared times 1/2 e to the 2x. Now the order that we typically write this in is coefficient, then polynomial, then exponential. So we'll say 1/2 x squared e to the 2x minus integral, and then we have v times du. So plug in v, 1/2 e to the 2x times du, which is 2x dx. Okay. Now, we have a 1/2 and a 2. Those will actually cancel each other out. And then we just have x e to the 2x dx. Our standard order would be to write the polynomial before the exponential. Anyway. So we look at that expression, integral of x times e to the 2x, and it really suffers the same problem that we had before. We had something that we just could not integrate. We have two different kind of functions here. They're being multiplied together. We have a polynomial times an exponential. Well, it turns out we have exactly the same situation in this case, where we have a polynomial times an exponential. So in this problem, we actually need to use integration by parts a second time. It won't always be required to do it multiple times. It just depends on the particular problem that we're looking at. In this case, we'll use u and dv. Now we still have a polynomial and an exponential, so with those two, polynomial is always going to be u, and then the exponential will be dv. That's a dx, sorry. Okay. We still have to find the derivative of u, which derivative of x is just 1 times dx. And the integral of e to the 2x, once again, is 1/2 e to the 2x. Okay. Well, here's where we have to be careful. There's a minus sign here, and then we're doing an integration by parts for this integral. So this integral, when we replace it with the integration by parts formula, that will be in parentheses with the extra minus sign outside. Excuse me. So this minus will basically distribute to both of those parts. So we want to be careful that we don't get any signs mixed up at this stage, after all the other work that we've done. So let's plug in. We have the same term here. This one's not going to change. But then we have minus parentheses u times v. So x times 1/2 e to the 2x. So let's say 1/2 x e to the 2x. Minus integral, and we have v times du. Now, v is 1/2 e to the 2x, and du is just dx, and so that'll be inside of our integral. Now, if we like, we can go ahead and resolve the minus signs, or distribute the minus basically. So we minus 1/2 x e to the 2x, and then plus, and then we think about what's the integral of 1/2 e to the 2x. Well, we already know the integral of e to the 2x is 1/2 e to the 2x times another 1/2 that we have here. That'll make it 1/4 e to the 2x. And then finally we can add plus c at the end. Okay. And so that would be our integral of x squared times e to the 2x. Now there is a different way we can do this that we'll learn in a little bit that can be a little bit faster in certain cases. Probably in this case it would be faster. Excuse me. So, but we'll get to that after we'll look at some of these other ones. It's kind of a very specific process that only works for a few types of integration by parts problems. All right. So let's look at another example. Let me start with this one. I actually wrote down 2 with logarithms, but let's just do the plain integral of the natural log of x by itself, since we've never done that before with the integral of natural log x. We could not do the integral of natural log of x without the integration by parts. Okay. Now, as far as we choose which one's going to be our u, again, LIPET. So if we have a logarithm, that's always our first choice for u, and we can see that's what we have here. We'll use u equals natural log of x. Now what we said before doesn't really hold true here, and that was that if we have a product of 2 different types of terms, we need to use integration by parts. Well, that is true, but the issue is we don't have a product of terms here. It turns out if we have natural log of x present in the integral, then usually it's going to be an integration by parts problem regardless, even if it's just natural log of x by itself like we see here. So if u is natural log of x, the only thing left is dx, and that'll be our dv. It's important that we take these differentials and include them in our expressions here. Now we need the derivative of u, which the derivative of natural log of x is 1 over x times dx. And the integral of dx is just x. So we have our u, our dv, our du, and our v finally. So let's put them all together according to our integration by parts formula, which was uv minus integral v times du. U times v, so natural log of x times x. Normally I would write the x that's being multiplied in front, so it's x times natural log of x. The reason we don't want to write that in the opposite order is that we don't want to confuse what's inside the natural log for what is outside the natural log. And that's why anytime we have x times a natural log or an exponential or a trig function, for instance, we put the polynomial term in front and then the special function afterwards, just to make sure we don't confuse this polynomial term as being part of what's inside the other special function, like we talked about here. And then integral v times du, so v is x, du is 1 over x dx. Okay. Okay. Now we can go ahead and we have x times 1 over x, so we can combine that. Just the x's cancel, so it's just a 1 times dx. So the integral of 1 is just x. And then we have our constant integration. And that's our answer right there. Now we couldn't have done that without integration by parts, but you know, it's not a overly complex integral even with the addition of integration by parts. But it is necessary to solve any integral containing a logarithm where it's not just even if it is just a u substitution, it's going to be one we end up having to do. Well, yeah, we have to check to make sure if it's a u substitution or not, because if it is u substitution, that's going to be way easier than integration by parts. So that's the other thing to keep in mind. But the only time we would be able to do u substitution here is if u is equal to natural log of x, and its derivative 1 over x was somewhere else as part of that expression. So we don't want to get carried overboard there. Yeah, just integral of natural log by itself is integration by parts. Okay, so let's look at our other log integral that I wrote down initially in our examples. Again, use the examples we started with. So we have integral log and integral x to the 4 times log. Now, we did this integral first, and it required 2 integrations by parts when we had x squared. When we just have x, that's going to require 1 integration by parts. But you might look at this x to the 4th and think, does that mean we need to do integration by parts 4 times? Well, in the case of natural log, luckily the answer is no. Okay. Let's look at how this one works out. The difference in this problem is because of the hierarchy of the terms. When we look at our order in which we would choose which function would be u, again, the logarithm has primacy over the polynomial. We would certainly choose it first. Okay. It's only when we choose the polynomial first that its exponent might be problematic and indicate the number of times that we'd have to do integration by parts. If this had been x to the 4th times e to the x, absolutely that means we do integration by parts 4 times. But x to the 4th times logarithm actually is not the case. Because we're going to let our logarithm be our u, because that certainly is what we would choose first. And then our dv would be the x to the 4 dx. That is the other part of what's here. So we have our u, and then we have our dv. But everything that's in the original integral should be a part of one or the other of u or dv. Okay. So we've selected our two terms, u and dv. Du, the derivative of natural log, we know is 1 over x dx. And then v, if we wanted to integrate x to the 4th, that would be power rule, so x to the 5th over 5. Now, let's see. From here, let's go ahead and plug that into our integration by parts formula. So we have u times v minus integral of v times du. And again, you'll need to memorize that. By the time you work through this homework set, you'll probably have that down pretty well. U times v would be natural log of x times x to the 5th over 5. Minus v times du, which is x to the 5 over 5 times 1 over x times dx. That's an x, sorry. Now we can go ahead and, looking inside this integral, we still have a product of two terms. The difference here is that we can actually combine these together, or actually reduce these if we want to think about it that way. Because we can multiply x to the 5th times 1 over 5 times x, and then reduce what we have from there. X to the 5th divided by x leaves us x to the 4th, basically. The other thing that we can do is we can take that 5 on the denominator and factor it outside the integral, so we can write a 1/5 on the outside. And then we just have an x to the 4 inside that we need to integrate. So we can go ahead and do that. So that is minus 1/5 times, and the integral of x to the 4th would be x to the 5th over 5 again. Then we have plus c still. So that's our constant of integration. That takes care of both parts, technically. The last thing we need to do here to simplify is just combine our terms here. So 1/5 times x5 over 5. So it'll be x to the 5th over 25, basically. Okay, and so that would be our answer. Okay, so even though we had x to the 4th to begin with, just because it's x to the 4th doesn't mean we're going to do 4 integrals, or 4 integrations by parts specifically. That does apply if x to the 4th is our u. In this case, though, because we had a natural log present in the original expression, we ended up choosing natural log of x as our u. That way we didn't get caught in that loop of multiple integrations by parts. Okay, let's move on. Now this next one I wrote down, we're going to run into some interesting times here. Integral e to the x cosine x dx. This one, let me move the paper down. This one we have a exponential function times a trig function inside of our integral. And again, we look at our order in which we choose which one's going to be u. And again, exponential is above trig, so we want to use exponential as our u, and then the trig function will be a dv. Now I said before that really these could be in any order, but the main thing is we want to maintain a consistent order. That's why we just want to keep using u equals the exponential function. If we just use the same order every time, we can't go wrong. And there's a specific issue that crops up with this problem where we definitely need to pay attention to that. So we said u is equal to e to the x. dv is cosine x dx. So we go ahead and find du. The derivative of e to the x is e to the x. And the integral of cosine x is sine x. Now we plug it into our formula, uv minus integral v times du. So that's e to the x times sine x minus v times du, so it's e to the x sine x dx. Okay. So completing that particular integration, we still have a product of an exponential and a trig function in this integral. Now, looking at that, you may have some suspicions about what's going to follow, because it looks like we haven't really changed much from the original integral. We still have e to the x times a trig function. We just changed which trig function we're working with. Well, the good news is the bad news is we have to do one more integration by part. The good news is that's all it's going to be, even though we're going to get to kind of a weird place there. Let's continue with our integration by parts here. Okay, for this expression now, because we have an exponential times a trig function, we'll choose the same hierarchy. Let u equal e to the x, and our trig function dv, and then we also include dx as part of that. Differentiate e to the x, that is e to the x, of course, dx. And then integrate v. Integral of sine is actually a negative cosine. We'll make sure we get that negative on there, otherwise this is not going to work. It's always important that we get the correct integrations and derivatives. And what makes this confusing for some students is that we all, at the same time we're doing integrals, we're also doing derivatives. If you don't have a great grasp of the two concepts, integrating and differentiating, then having to do both in the same problem can be confusing. So we want to make sure as we go through this that we are actively paying attention to which direction are we going. Are we differentiating or are we integrating? And so we want to make sure we choose the right path and accurately complete these processes. Okay. So we took, well, either way, when working with e to the x, we know both the integral and the derivative are e to the x, so there's really no surprise there. The main concern is actually going to be with the trig function, because it does change as we integrate or differentiate. Now, like we had on the first problem we looked at, we do have this minus sign here and another integration by parts. So we're going to have e to the x sine x minus parentheses uv minus integral v du. Now if you would like to take care of that right away and put minus uv and then a plus integral of v times du, we're certainly welcome to do that. The order is not really important. Personally, I like to go ahead and complete what's inside the parentheses here and then distribute the minus sign, just to make sure we have a nice order for everything. There's no right and wrong there. Either one works fine. In this case, v does contain a negative, so that's going to make it a little more interesting on top of everything else. We have to keep track of our signs. So u times v would actually be a negative e to the x cosine x dx. I don't know why I have dx. That was throwing me off there. I don't know. Sorry about that. When we integrate, we don't need dx. Dx goes away because it's part of the process. Anyway, sorry. And then minus, we have integral of v. Now, v itself is negative. So we have negative e to the x cosine x dx. I'm off screen. Let me fix that. There we go. So we have two negatives here already, so that's going to turn into a positive. And then this negative is going to distribute and make that a positive, and then this positive will then become negative. It's three negatives is still negative. Any odd number of negatives is still negative. Alright, so resolving all of our signs, we end up here. Now, some of you may notice a problem. Not necessarily a problem, but certainly a concern, I would say. And it's very concerning that if we think back to where we started in this problem, we start with the integral of e to the x cosine x dx. And currently, we've arrived at the integral of e to the x cosine x dx with other terms now. So not only have we not integrated e to the x cosine x, we've made it worse from one point of view. And definitely that's concerning, but this is something that we don't often have to do with integration, but it's specifically a technique that we need to use for certain integration by parts problems. We've been using like these equal signs here, just to show that we're continuing from the original problem. That's equal to this, which is then equal to this, which is then equal to this. If we think about what's on the left-hand side now, the left-hand side is the original integral that we began with, which is e to the x cosine x dx. That's our original integral, so I'm going to call that I. Okay? Just to have something to represent that rather than writing that down again. So if we call that I, then we have e to the x sine x plus e to the x cosine x minus, and this is actually the same thing as I. Okay, so we actually have I over here also, but it's now subtracted. Okay, so what we can do, we can think of this as an equation and say if our goal is to solve for I, is we want to solve for the integral of e to the x cosine x dx, then currently we have I on two different sides of the equation. So let's combine our like terms and then solve for I. Okay? So essentially what's happening is we're adding I to each side of the equation. So we can say I plus I is 2 times I is equal to e to the x sine x plus e to the x cosine x. And then to solve for I, we can divide by 2. So I is equal to 1/2 e to the x sine x plus 1/2 e to the x cosine x. Okay? And I is actually the original integral we started with, so this is our answer then. And of course we need plus c, or constant of integration, in there. Let's not forget that. But the main part of it, though, is based entirely on that process where we take this, move it over to the left-hand side, and then divide by our coefficient now. Now, if we had gotten to a point where if we had made a mistake with our signs and said this is a plus instead of a minus, then we would have canceled out the i's and we just would have been at a loss at that point, because we would have had a statement that meant nothing, which is false in this case. But technically it'd be true for certain values, but not true for entire equations. But anyway, the point being that sometimes we'll have to use this particular technique of not forgetting what our original integral was, and then using that and arriving at that particular integral again in the process of solving our integration. By letting that interact with the original integral, we're able to set up a situation where we can actually solve for the original integral by using like terms and then dividing by this constant. Okay. Alright. From there, I'm going to go ahead and do the integral of secant cube because it actually uses that same technique. Now, in section think it's section 3. We actually will look at more of this type of integral where we have secant or tangent or sine or cosine where it's raised to a power. Well, any of the trig functions really. But this is such a unique one. We like to work it into this section with the integration by parts. The integral of secant cubed. Even if it was cosecant cubed instead of secant cubed, it would be the same kind of problem. Because secant and cosecant more or less behave the same. It's just slightly different functions. But what we end up having to do is we'll split up our secant into secant x times secant squared x dx. Okay. Now, secant squared x, hopefully you recognized secant squared as being the derivative of tangent of x. The derivative of tangent x is secant squared x dx. And so when we split this up into u and dv, it's not according to our chart anymore because both of these are trig functions. We have to think of it in terms in which trig function can we integrate. The integral of secant squared is much nicer than the integral of secant. The integral of secant is like a logarithm expression. The integral of secant squared is exactly tangent x. So that's probably the better one to go ahead and use here. So we'll use secant x as u and secant squared x as dv. Now the derivative of secant x is secant x times tangent x dx. And then if dv is secant squared x dx, the integral of that we know is tangent of x. So we'll put those together. We know we need u times v minus integral v times du. Now uv is secant x times tangent x. V times du would be, we have a secant x and tangent times tangent, so tangent squared x. Dx. Now we look at this expression and we have secant times tangent squared inside of our integral now. The question is, how can we split that up in a meaningful way? And that's a good question. One thing we can do, and this is something that whenever we're working with trig in particular, something that we want to keep in mind is that we could use an identity of some kind to help us sort this out. So in this case, we can think of this tangent squared. We can look at our tangent squared of x. And yeah. We have an identity that says tangent squared of x is equal to secant squared of x minus 1. Okay? That's one of our three Pythagorean identities. Or based on the fact that sine squared x plus cosine squared x is equal to 1, we just take that equation, divide everything by cosine squared, and we come up with this equation. Moving things around slightly. So let's go ahead and do the substitution, and we should be able to simplify from there. So we actually don't have to do a second integration by parts, but the reason I wanted to do this after the e to the x cosine x problem is because of that last part of that problem where we had to interact with this equation on the left hand side. You'll see where that comes out in a second. We can distribute the secant x here. So we have secant x tangent x minus integral of secant cubed x minus secant x dx. Now, this subtraction certainly distributes to both parts inside, so we can make it secant x tangent x minus integral of secant x, or secant cubed x dx plus the integral of secant x dx. Now, if you don't recall, and it's likely that you may not recall, which is perfectly fine at this stage, the integral of secant x is actually natural log of secant x plus tangent x. The other thing is that on this left-hand side, don't forget the original integral that we started with was secant cubed x dx. So, once again, we have the situation where we have identical integral here as we have here. So let's go ahead and call this I. We'll leave this as secant x tangent x minus I plus, and again, the integral of secant x is natural log of secant x plus tangent x. For this, I really should be using absolute value bars instead of parentheses. But I'm not usually a stickler for that, but because a lot of the times where we have to use that, it's generally a positive value anyway. However, secant plus tangent is by no means guaranteed to be positive, so it's nicer to put the absolute value bars there. Anyway, so we have minus I, so we can add the I over to the left-hand side. So 2I is equal to, we have secant x tangent x plus the natural log of secant x plus tangent x. Finally, to get I by itself, I is equal to, we should divide by that too. So it's 1/2 secant x tangent x plus 1/2 natural log of absolute value of secant x plus tangent x plus c, so we don't want to forget that. Okay. Now that will actually complete our integration because we solve for I, which is our original integral of secant cubed x. So this one only required one integration by part, but then we had to apply an identity, and then we had to interact with the original problem on the left-hand side in order to solve for this integral. It's a little bit of an unorthodox approach, but for problems such as this and the last one, it's absolutely necessary to be able to solve this. If we didn't do this, we'd end up in an endless loop of integration by parts where we'd never actually arrive at the answer. Okay. Because if we go back to the other problem, which has disappeared somehow, here we go. If we come back here, if we did another integration by parts, a third integration by parts here, we could do that, but we'd just, it'd just be an endless loop, because we keep coming back to a term such as this, either e to the x cosine x or e to the x sine x, depending on which stage of the or whether we were at an even number or an odd number of integration by parts, and it would just be endless. And so by interacting with this left hand side and this right hand side, just letting those move over, we are able to actually solve for what the original integral is equal to based on that. So that's a useful technique. Okay. All right. We still had some other integration by parts problems I wanted to look at. These do not require multiple integration by parts or special techniques. It's just a standard problem that I wanted to discuss. Okay. You'll notice that none of these that I've done are definite integrals. The only thing that definite integrals bring to the table is after we finish our integration, we just plug in the limits of integration. So I think we're okay with that by now, but let me know if you do have any questions on that. Here we have a polynomial x times a trig function cosine of 2x. So again, going back to our hierarchy, we know that our polynomial, we would actually choose to be u before we choose either a trig or an exponential term. So in this case, it'll be our polynomial is u, so we'll let u equals x. And then dv will be the remaining parts of the integral, which is cosine 2x dx. We then calculate du, or find du, which is just 1 times dx. And we also integrate cosine 2x, which is 1/2 sine of 2x. Remember, when we integrate, we divide by that derivative inside the function. So we divide by the 1/2. So, or we divide by 2, which is the same thing as multiplying by 1/2. Alright, so we know it's going to be u times v minus integral v times du. Probably by now you're probably sick of hearing that, so you might have it memorized already. I would recommend going through and doing the homework, and after that you'll probably have a pretty concrete memory of that equation. Sorry about that, Mark. So 1/2 x sine of 2x, that's u times v, and then minus, and then v times du is just 1/2 sine 2x dx. Okay, now we just have to complete this integration over here. So 1/2 x sine 2x minus, and then the integral of 1/2 of sine 2x will actually be a negative 1/4 cosine of 2x. Okay, so the integral of sine is negative cosine. Keep the angle the same. But since the derivative of the angle is 2, we divide by 2 when we integrate, which makes that a 4 on the bottom instead of a 2. So one last rewrite of the answer, so 1/2 x sine 2x. This will be a plus 1/4 cosine 2x. And of course plus c. Okay. For the last of these examples, let's look at and this is actually, let's go ahead and do it a definite integral. I said we didn't need to necessarily, but I think it'll be nice. Not arcsecant, arcsine of x squared dx. Let's do integral 0 to 1 of x times arcsine of x squared dx. Now, arcsine of x squared. Let me just throw up a formula here. Y equals arcsine of u. If we have a like this format as for our equation, then y prime would be, what would it be, du over square root of 1 minus u squared. Okay. So the derivative of arcsine of u, or inverse sine of u if you prefer, would be du over square root of 1 minus u squared. And we just, whatever u is right here, and then whatever the derivative of u is right here. Okay. So the u in this case would be the x squared. So if we wanted to differentiate arcsine of x squared, we would get derivative of x squared, which is 2x, over square root of 1 minus x squared quantity squared, which would be 1 minus x to the fourth. Okay. This one's going to be kind of weird. Anyway. Now, the reason I talk about that is because we look at our hierarchy of choosing which one's going to be u and which one's going to be dv. And because we have an inverse trig function, we'll actually choose that prior to the polynomial. Because we have polynomial x times an inverse trig function arcsine of x squared. So definitely the inverse trig function will be our u in this case. Okay, and so I'm going to go back to what I said. Du would be 2x over the square root of 1 minus x to the fourth dx. Okay. Again, that's based on our pattern here. U is x squared, well, whatever's inside the arcsine function, x squared. Its derivative goes on top, so that's 2x. And then 1 minus u squared, so 1 minus x squared, which would be x to the fourth. Okay, and so that leaves dv as x times dx. So here's our u, and then dv is outside of that. And then the integral of x is 1/2 x squared. We'll make sure we complete that power rule. Alright, so u times v, I'm actually going to put 1/2 x squared first, times the arcsine of x squared, minus integral v times du, so 1/2 x squared times 2x over the square root of 1 minus x to the fourth dx. Alright, our 1/2 and our 2 will certainly cancel out. It's 1/2 times 2 is 1. And then we have x squared times x. We can go ahead and make that an x to the third on the numerator. I am going to go to another page, though. Here's the back. Okay. So we have 1/2 x squared, arcsine of x squared, minus integral, and from here we'll have x to the third on top over the square root of 1 minus x to the fourth on bottom dx. One thing we don't want to lose track of here is that we are working with a definite integral from 0 to 1. But we may choose not to worry about that until we complete the integration, which I recommend. focuses on completing the integration first, and then we go back and make sure if it's a definite integral, we're able to plug in the limits of integration and evaluate. So, if you want, you can make sure you put the limits here, 0, 1, and then technically all of this would be in that box with the limits also. So, if you want to use that to make sure you don't forget, that's certainly recommended. Okay. The question then is how we deal with this particular term, this particular integral. Because now, it doesn't really fit our integration by parts, because we said integration by parts was a product or quotient of two different types of functions. And the 5 functions that we outlined are logarithms, inverse trig functions, polynomials, exponentials, and trigonometric functions. Now this one certainly includes a polynomial, but it has a square root, which we call an algebraic term. In fact, x cubed is also part of the algebraic terms. So instead of having a product or a quotient of two different types of functions, we actually have just an algebraic function to integrate. So, all in all, what that tells us is that we can't use integration by parts on this remaining integral. So, what I would say instead is let's look for some kind of substitution that we could possibly make. We're just working with x's, so our variety of experiences are not large here as far as different techniques that we could use. So I would say let's go ahead and look for a substitution that could be made. Whenever we look for a substitution, don't forget we're looking for, is there one term in the problem that's a derivative of another term in the problem? Specifically, if we have like parentheses or square root where something is raised to a power, can we substitute for what's inside that delineator, either the square root or the parentheses? Turns out all of that is true in this case. Our expression under the radical is 1 minus x to the fourth, and if we think about the derivative of 1 minus x to the fourth, we know the derivative of 1 is 0, but x to the fourth is negative 4x cubed, and the x cubed is already up here, which is great because that'll let us complete the substitution. Now we look at what we have in this particular expression. We have an x cubed and a dx. So if we want, we can take du and take this negative 4 and divide it over, and we'll let that replace the x cubed dx. Okay. So completing the substitution, x cubed dx, kind of our numerator, that'll be du times, or divided by negative 4, which is the same thing as times negative 1/4. So what I did, instead of saying du over negative 4, I took the negative 4 and factored it out on the outside, so it's actually a negative 1/4 on the outside of the parentheses, or of the integral, sorry. On the bottom, we know that this expression is u, so it's just square root of u. So that'll actually change that to a positive, is what that really amounts to. And inside, we can think of that as u to the 1/2. Because it's in the denominator, it would be u to the negative 1/2 power du. So normally we know square root of u, square root means a 1/2 power, but because it's in the denominator, it would be a negative 1/2 power. Okay. So continuing, this side, we could actually resolve this first part any time we choose. just plugging in the 1 and the 0 respectively. I kind of want to save that to the end though. Now integrating u to the negative 1/2, remember it's a power rule, so we add 1 to the exponent. So u to the positive 1/2 divided by 1/2. Now dividing by 1/2 is the same thing as multiplying by 2. So we think of it, instead of dividing by 1 over 2, we multiply by 2 over 1, the reciprocal. And so we end up with 1/4 times 2 over 1 if we try to resolve this pair of fractions here. And then 1/4 times 2 over 1 is just 1/2. So plus 1/2. And then we have u to the 1/2, which is the square root of u. So that's square root of 1 minus x to the 4th. If we go back and look at our u substitution, and that's from 0 to 1. Finally, we're at a point we can plug in our limits of integration. So now we can plug in our 1 for x in both terms. So plugging in x equals 1 gives us a 1/2, 1 times arc sine 1, plus a 1/2 times square root of 1 minus 1, which is 0. Okay. Minus, plug in the 0, so we have 1/2 times 0 times arc sine 0. Doesn't really matter what arc sine of 0 is, which is 0, incidentally. But this is 0 as well, which zeroes out the whole term. Minus 1/2 square root of 1 minus 0, which is just square root of 1. So then we think about, okay, what is the arc sine of 1? The arc sine of 1 is the sine of what angle is equal to 1. It turns out sine of pi over 2 is equal to 1. So it's 1/2 times pi over 2 minus 1/2. So our answer here is pi over 4 minus 1/2. And that is our actual value for this particular integral. Okay. So including the limits of integration doesn't really alter a whole lot because we already know how to plug those in. The only thing that's a little bit different here is we are working with an inverse trig function, so unless we're really comfortable with the trig function values, it may be something that you want to try to put in your calculator, which is fine. Arc sine of 1, you'll be able to look that up and get pi over 2. Or your calculator may say 1.57, whatever, if it's a decimal approximation. And then arc sine of 0 is 0, but it doesn't matter because it's whatever we get for plugging in 0 is zeroed out by this becoming 0. Anyway, not a bad problem. There's one other thing that I want to look at today. This is what's called the tabular method. This is an alternate method for solving these integration by parts problem. The only catch is that it's only usable. That might be a better way of saying it. It's only usable when u is equal to x to a power. Okay. So our u has to be a polynomial term, basically, for this to work. If u is anything else, if it's like a trig, or sorry, inverse trig, or logarithm, or even a trig or an exponential, then we won't be able to apply this. For example, that may be a little extreme, but let's go with it. The integral of x to the fifth times e to the x dx. Now you may recall from the first problem that we did, we integrated x squared e to the 2x, we had to complete two different integration by parts, here and here. And that was because we actually had x squared, so the exponent really tells us how many integration by parts to expect in a u equals x to the power problem. So this, being x to the fifth, tells us that working this by hand, we'd have to do integration by parts 5 times. Well, that may take a while. It may take the better part of an hour, depending on how lost we get in all the x's and the e's and the powers. And it doesn't sound interesting at all. It doesn't sound entertaining, doesn't sound informative. It's just busy work, really. Now, the way that we can work around that is with this tabular method. Okay, tabular method is nice because for these processes where it's really just a repeated application of the same integration by parts problem. You know, when it's x to the fifth, we use integration by parts, it reduces it to x to the fourth. We do integration by parts again, reduces x cubed, and we keep going with the integration by parts until we just have e to the x being integrated, which takes 5 times in this case. So it gets boring. It gets repetitive. Okay, we can do it, but there's easier ways, it turns out. We can automate this whole process with what's called the tabular method. So first, we still need to identify what is going to be our u and what is our dv. I'm going to pick two relatively easy terms here just to for the purposes of this demonstration. So what we're going to do is we're going to make 3 columns, here, here, and here. And I'm going to put 3 headers up here. I'm going to start with u first. And what we're going to do in this column is we'll start off with our x to the fifth. And we'll keep taking derivatives until we get down to 0. So 5x to the fourth, 20x cubed, 60x squared, 120x, 120, and finally 0. Okay, so we differentiate all the way down until we get to 0. Next, our last column will be dv, which is e to the x dx. We don't even really need to worry about the dx here. We know the dx is there. We just want to take this expression and integrate it until we get to an equal number of steps that we did here. Integral of e to the x is just e to the x, so this is just e to the x all the way down. Okay. Now the first column I haven't talked about yet. First column is just pluses and minuses alternating back and forth. We're going to start with a plus, then a minus, then a plus, then a minus, then a plus, a minus, and then a plus. We're basically filling it out to the same level that we did here. The reason this tabular method works is if whatever polynomial term that we have, like x to the fifth power, eventually if we take enough derivatives, any polynomial becomes 0. And the fact that u eventually becomes 0 is the key to this. That means we can stop, basically. That's why it wouldn't work if u is equal to a cosine of x, for instance, because if we keep taking derivatives of cosine x, we never actually stop. We never get to 0. We never settle on one term. Now the last thing we need is the pattern of how we're going to combine these in order to create our answer. And the pattern is we go across and down, across, down, across, down, and we repeat that until we get to the end. Notice that we do not use the 0 at all, and actually we don't even need this last plus for that matter, but I like having the 0 there as kind of a benchmark as how far we have to go with our columns. So what we do is we know our first term will be a positive x to the 5th times e to the x. Okay, so our integral of x to the 5th e to the x dx. So we're going to have a positive x to the 5th e to the x. We're going to have a negative 5x to the 4th e to the x. We'll have a positive 20x cubed times e to the x. Minus 60x squared times e to the x. Plus 120x e to the x. Minus 120 times e to the x. And finally, plus c. And so without doing 5 integrations by parts in a row, we're able to use this tabular method to achieve the same outcome, but in a much more timely manner. The main thing to memorize here is the pattern. Once, how do we create our table and how do we use our pattern from there? This method will work even for that first problem we did where it was x squared times e to the 2x. This pattern will work. Anytime we have to do integration by parts more than once with a u equals x to a power, absolutely I would recommend the tabular method as a good alternative there. Okay. Let's do one more example here, just to kind of make sure we're okay with this. I'll do a shorter one. I won't do x to the 5th. Let's do, for example, integral of x cubed sine 2x dx. Now we know u is going to equal x cubed here, and dv will be the rest of it, sine 2x dx. And so we set up our table. Our u is in the middle, that's x cubed, 3x squared, 6x, 6, and 0. So we just take our derivatives down from there. dv, we start with sine of 2x, and now we integrate. This one we differentiated, this one we integrated. Integral of sine 2x, negative 1/2 cosine 2x. Integral of negative 1/2 cosine 2x is negative 1/4 sine 2x. Integral of negative 1/4 sine 2x is positive 1/8 cosine 2x. And the integral of 1/8 cosine 2x is 1/16 sine 2x. Positive. Okay. And again, we go plus, minus, plus, minus, plus, across and down, across and down, for each of these terms. Okay. So you get the idea, hopefully. So let's write our answer out. So we get x cubed times negative 1/2 cosine 2x minus 3x squared times negative 1/4 sine 2x. So minus 3 times minus 1/4 would be positive 3/4 x squared sine 2x plus 6x times 1/8 cosine 2x. 6 times 1/8 is 6/8 or 3/4. So plus 3/4 x and cosine 2x. Then minus 6 times 1/16 sine 2x. 6/16 is 3/8, so minus 3/8 sine 2x, and of course plus c. And so that would be the result of our integration. Normally it would take 3 integration by parts to arrive at that conclusion, but again the tabular method shortens it significantly. So I think it's very nice when we can use that. But again, we can't go overboard. We can't use it if it's not allowed, basically. It can only be used in integration by parts problems where our u is going to be a polynomial. And if u is equal to x, I would just do normal integration by parts. But if u is x squared or x cubed or larger, then I think tabular method is a really nice way to go there also, instead, I should say. Okay. Let's look at some homework. My book back in here. All right. So this is on page 529. Fifteen, 17, 19. Seven, 31, 33, 45, 51, and 53. So go ahead and look at those for homework, and we will continue Chapter 8 from there next time. So we'll start section 8.3 and probably, well, we'll do 18.3 for sure, and then probably part at least of 8.4 on Thursday. Okay. Make sure you finish the second part of your test by tonight if you haven't already. I know there's a few of you that still need to turn that in. And as I said, I probably won't have the test graded until next Tuesday. But you'll see them being updated as the week goes on. Generally, I'll try to sit down during my office hours to grade those, but we'll see how it goes. So, all right. Well, you all have a good day, and hope you're all doing well. It's been basically me lecturing this class, so I hope everyone's alright, and just maybe you're a little tired, which is fine. But take care of yourselves, and I will talk to you next time. Bye.